Hey guys, welcome back to Genius Learning. In this video, I want to take a look at an E&M problem. All right, and this is the visual, the situation. We have a linear isotropic homogeneous dielectric sphere of radius A, and it contains free charge all along the density, and the density is rho naught. It says find the dielectric displacement, electric field for all points inside the sphere. Excuse me. Find the total energy of the fields inside of the sphere. What is the total bound volume charge? Find the potential due to the system for all radius, and what is the potential at the center of the sphere? A lot. So let's start one thing at a time. We have this sphere and we have density rho naught, okay, uniform density, and this is just a view. If I split the sphere in half, all right, it shows that, you know, all throughout rho naught exists and the radius A. Okay, so let's start with the first question. We have find, let's see where I'm gonna put this. All right, so find dielectric displacement, electric displacement, sorry, that's denoted by D vector, and electric field for all points inside the sphere. So for all the points inside the sphere. Okay, so first we're going to want to use Gauss's law to find the electric displacement. Okay, so we're going to use Gauss's law for dielectric displacement, which is D dotted with differential area equal to charge free enclosed. All right, so on the left side, since we're just considering a segment on the surface, okay, we're gonna have, let's see, this is what we're gonna use, and our two integrals are gonna be 0 to pi, 0 to 2 pi, okay, dielectric, and the differential area, okay, which is gonna be r squared sine theta, d theta, d phi. If you don't know how to get this Jacobian, I've made a video on it, deriving how to get this for surface charge and bound density. So refer back to those. And then the other side, which is Q free enclosed, we have this equation. Q free enclosed is going to be volume integral of the bound charge that exists in d tau, differential volume. So what is the bound charge that exists? And here we're going to express that with three integrals. All right, we're going to have 0 to 2 pi, 0 to pi, and then here, since we're only looking for points inside the sphere, we're looking from 0 to r, because 0 to A is the outside, and we want something right around there. 0 to r, it's less than A. So 0 to r, and then we have, the only bound charge that we have is rho naught that exists everywhere. And then our Jacobian, r squared sine theta, and this time we include dr, d theta, d phi, because we have a volume. Okay, so this entire thing, so this side here, we're going to just get solid angles 4 pi, and then the r squared stays, so we get 4 pi r squared. And on this side we're going to get, let's see, we got 4 pi from the solid angle. Okay, rho naught can come out. Okay, and then we have to integrate r squared dr, so that's going to be r to the third over 3. Okay, so then let's see, if we pass this to the other side, we're gonna cancel the 4 pi, we're gonna cancel the r squared, and we're gonna be left with electric displacement is gonna equal rho naught r over 3, and that's in the radial direction. Okay, perfect. So this is inside where r is less than a. Okay, so we found one. Now let's find the other. Electric field. So let's use the equation. Electric field is equal to electric displacement divided by epsilon. Okay, and I wrote the definitions here. For epsilon is the absolute permittivity. So if we're outside, we're gonna have different permittivity than if we're inside a dielectric, and these two are gonna represent that. And so all the quantities here, all right, represent the electrical properties of the material. So each one will tell you something different about traveling through a dielectric material. So specifically here, this is a general form, and it only changes whether we're inside or outside the material. In this case, we're inside. So let's take a look to see what happens. We got electric field is going to equal the electric displacement, which we found, over epsilon. So we have electric displacement 3, and then epsilon, right, r hat. And since we're inside, we need to change it to ke epsilon naught. So that describes what's going on inside of our dielectric. So this is really equal to rho naught r over 3 ke epsilon naught. That's in the radial direction, and this is inside where r is less than a. Okay, perfect. So first question down. We might do 2 videos for this because it asks a lot of questions for one problem, but they're very good involved questions that help you learn a lot about this chapter. So the next one is going to be find the total energy of the fields inside the sphere. So find the total energy, keyword. So total energy of the fields inside. We'll just put inside, and we're going to use the equation lowercase u e is equal to electric displacement squared over 2 epsilon. Okay, and this is energy density. Okay, so it's not the total energy. This is just the energy density. And there's other forms of this equation. There's 2 or 3 other forms, but we already found the electric displacement, and we found the electric field. So we could have used either one. The other one has the same kind of form, but with electric field represented. Okay, so I'm gonna choose this one, and we have those values. So we're gonna get lowercase u, okay, which is energy density, is going to equal rho naught squared, right? I'm going to put this d in there. I'm going to have rho squared, r squared. I'm going to get a 9 from here, and I have a 2 here, so that's going to be 18, and then epsilon, right? But we are inside the dielectric. So this epsilon, which is the absolute, needs to be changed to describe specifically what's going on inside of our dielectric. So we're going to change this epsilon, and we're going to represent it with Ke, which is the dielectric constant, and epsilon naught, it's permittivity, free space. Okay, and we need this one, right? Because the ultimate energy, or the total energy that we're looking for, is capital U E equals the integral over all space lowercase ue d tau, so volume integral. Okay, so it might be a little confusing. I got a little confused at first. Lowercase, uppercase. This one's uppercase for the total, and then the lowercase, which is the energy density, goes inside the integral. And if you think about it, it makes sense, because you have to integrate over the entirety of the volume, and you want to know all the energy densities in there, and so that'll give you the total energy. So putting it into this equation, we get, see, I already messed up. Uppercase U, okay, uppercase U is going to be equal to 3 integrals, right, because it's a volume. So 0 to 2 pi, 0 to pi, and the most important integral right here, we want to know that total energy from here all the way to the surface. So 0 to a. All right, so this one is usually the integral people mostly mess up on, the r, the radius, right? Because the other two are usually just the same. And then we got this value for lowercase ue, so let's put that here. Okay, and then we got the Jacobian, which is r squared sine theta dr d theta d phi. Okay, let's see, what can we pull out? We got enough space here, yeah. Okay, so let's see, we got capital UE. We can take out the solid angle, right, which is 4 pi, and then we could take out rho naught. We can take out the 18 on the bottom, the Ke, and the epsilon naught, and we're left with just the integral from 0 to a of r squared dr. Right? Let's take a look. So this, so these two combine, the r squared and the r squared. So you have an r squared here that came from your energy density, and then the Jacobian itself had an r squared, and so you combine those two to be r to the 4th before you integrate. Okay, so now we're gonna get, let's move it up here. We're gonna have total energy is gonna be equal to, if we evaluate this integral here, let me just write it out. So I'm gonna keep these values here for a second. So I'm gonna have 4 pi rho naught squared 18 Ke epsilon naught, and this integral here is just gonna be a to the 5th over 5. So a to the 5th over 5. So let's simplify this first. This is gonna be 2, this is gonna be 9. 9 times 5 is 45. So we got total energy is gonna be 2 pi rho naught squared a to the 5th over 45 Ke epsilon naught. And this is total energy. Okay, so whenever you're asked to get total energy, remember that you're gonna have to integrate. So if the formula you have doesn't involve an integral, it's not the total energy. It's just describing an energy at a certain area, or maybe the energy, you know, up to a certain surface. So we got the total energy. All right, do Do I have room? I might have, okay, let's do total bound. So let's box this up. This was the second thing. All right, now let's find the total bound volume. The total bound volume charge. Okay, so here we go with the total again. All right, and so some of the equations that we can use, because first of all, find the total bound volume charge. What is the equation for that? We have volume bound charge is equal to negative gradient of the polarization, P, and that involves us finding P. So now let's look for an equation that has P in it that we can use because we have electric field and electric displacement. So we can use electric displacement is equal to epsilon electric field plus polarization. And if we rearrange this, right, we put the epsilon naught and the E on this side, we're gonna have polarization. It's gonna be equal to electric displacement minus epsilon naught electric field. So now we have an equation for P that we know the values for because we have D, we have E inside. We could find P, then we can put it in here and find our bound charge. Okay, so let's see. We're gonna do P. Let's plug in what we have for the electric displacement, and that's gonna be rho naught R over 3. Okay, this is in the R hat, and minus epsilon naught, and for electric field we have rho naught R over 3 KE epsilon naught. So these epsilon naughts can cancel. This is in the radial direction. Okay, and that's it. If we combine this or simplify it, we're gonna have, let's see, we could pull out a rho naught from both of them. We could pull out R and a 3. And then inside we're gonna have 1 minus 1 over KE. So combine the bottom and do a little algebra. And we have this. All right. So I'll do it here on the side. So what we had in there was 1 minus 1 over KE, and lowest common denominator, and then we're left with that, which is what I got here. Okay, so this is, oh, we're forgetting the R hat. Okay, radial direction. This is a vector. And so we have this for polarization, and now we're in a good position to plug this in to here to solve for our volume bound charge, but this is not the total. All right, so let me make another video here and continuing this problem. Give me some more room here.